Hi, my name is Stephan T. Lavavej, and since 2007, I've worked on Visual Studio's STL implementation licensed from Dinkumware. So today I'm going to talk about 4 or 5 STL features in C++14, and one or 2 of them are in C++11 as well, that we've implemented, plus some of the implementation techniques we've used. So you'll be able to use all the features in your own code, and hopefully some of the techniques will be applicable too. Now, because I work on Visual Studio, I'll be presenting snippets of our implementation, but everything I'm going to talk about is portable. So you can use it on other platforms as soon as they've implemented C++14. Also, because there are tons of you and only one of me, if you have questions, please hold them until the end. You'll notice I have cool slide numbers. So if you have a question, just write down the slide number on your silenced computing device, and then mention it to me at the end, and we can go back and talk about as much as you want. OK, so first thing, I'm going to start off pretty simple before I get to things that blow your mind. Let's look at user-defined literals and inline namespaces. These are 2 core language features that work together. These core language features are in C++11, but there was no standard library support until C++14, and then that was added. So let's look at usage of the standard user-defined literals. So now I can say things like double quote per, double quote suffixed with a lowercase s. And what this is that actually is a stood string temporary object. It is exactly equivalent to if I said construct stood string, paren, or brace if you like, double quote per. So there's no efficiency advantage or disadvantage. It's constructing something at runtime. It can't be evaluated at compile time, nothing like that. But it's very convenient. Sometimes you do need a stood string. Here I'm using it to concatenate. Or you could pass it to a template and get template argument deduction. But it's not limited to stood string. I can also use it with the chrono library. This is exceedingly useful. So I could do something like this thread sleep for 15 ms. And that would sleep for 15 milliseconds, which maybe I don't want to do in my program, but whatever. There's UDLs for nanoseconds, milliseconds, all the chrono units that come along. And if you were not permanently scarred in college by your complex analysis course, you can also use complex user-defined literals. So you can say 3i, 5.7i, and get a complex float double or long double out of there. I have a ridiculous story to tell, maybe offline, about how long it took the committee to standardize floating complex literals with the suffix if. Think about that for a moment and how hard that is. Very annoying. So this is what usage looks like, very simple. How are these things provided by the standard? Well, let's look at their declarations, because there's a funny little trick that's going on in the standard. So here, I'm just depicting the declarations. The implementations are very, very simple, of what the stood string literal looks like. So there's namespace stood, and then a nested namespace literals, and another nested namespace string literals, and then you got this operator double quote s. Operator double quote is what a user-defined literal looks like. And the fact that it takes const star and size t means that I take a string. Of course, you need to include the string header for this. You don't get it automatically. The chrono literals are very similar. You include the chrono header, and they're in stood, literals, chrono literals. And then you've got h, s, ms, us, all that stuff. And complex literals are very surprising. Stood literals, complex literals. Oh, and by the way, because chronos types actually live in a sub-namespace, there's this other extra little trick where they reopen the chrono namespace and then they have a using directive. So there's like 5 different parts going on here. Namespaces within namespaces within namespaces, using directives. And what does this mean, especially if you want to write your own user-defined literals like under kg or underscore degree or whatever. So the way that you use these things is you might look at these declarations and say, OK, I need a using directive because these literals aren't accessible until I drag them in. So I should probably say stood literal string literals to drag them in. Please do not do this. This is unnecessarily verbose. It's not harmful. It won't hurt your code. It'll totally work. And it's not risky. It's just verbose. This is not how it's intended to be used. Instead, if you look at these declarations, I've highlighted in blue the fact that the sub-namespaces are inline. And what an inline namespace does is it drags everything inside it, and it appears as a member of the outer namespace. So everything in stood literal string literals is also accessible through stood literals, and it's actually a 2-step process. So if I say using namespace stood string literals, this is very focused. It says, OK, I need a using directive to drag these things in, But we know that using directives are very bad, and I certainly don't want these in a header. But even in a source file, I might not want to drag in all stds. So if I say std string literals, I drag in only the std string literal, but not the complex literal, not the chrono literal, and certainly not the types that are in std. But that's actually very, very restrictive, and it's actually usually OK to say, OK, I would like to use all of the standard user-defined literals. So if you say using namespace std literals, as long as you've included the necessary header, you have access to the string literals, the complex literals, and all that. But it goes further. If in a source file or within a function you've said using namespace std to drag in all the types, you also get all of the literals for free. And this is because inline namespaces have successfully dragged these declarations visible within std itself. And if you say using namespace std chrono, you get only the chrono types, but also the chrono literal. So the principle here is not obvious at first glance, is that you should be able to use a very fine-grained using directive to get just the literals that you want. But also, if you've used a using directive to drag in types, naturally you should also get the literals. If I've been so aggressive in my source files to say, OK, I want to drag in just std string and std vector, we should also give you the string literals. That's not going to hurt any code if we do that. So if you're defining your own literals, namespace, my company, and then some literal for that, you should probably provide them in an inline nested subnamespace so people can drag in just those literals, or if they drag in the type, then they also get your literals automatically. OK, so that was a nice simple feature. Now let's go on to another CS+14 feature, a few new algorithms. Oh, and this is some audience participation. I want to ask your opinion and guesses on some of these things. So here's an example of a few vectors initialized with the initializer list. We've got a couple vector strings. We've got a vector const char star. So let's start off. I want to compare to see whether the strings, the vectors TOS and DS9 have the same content, so that they're the same size and that all of their elements are equal. So what should I use to do this? Any guesses? Anyone? Shout it. Equal. Yeah, the title, the section slide said equal. No, I should not call equal here. TOS and DS9 are of the same type, vector string. Vector overloads operator equal equal. So you should write TOS equal equal DS9, and this will do what we expect. All of the standard containers overload operator equal equal like this. So list, if you're using a list, which is horrible for perf. So now let's put that aside. Now I want to look at TOS versus humans, also two vectors. How do I compare these things? You might be like, oh, I'm just going to say, operator equal equal. Well, that won't compile because their element types are different. And vector overloads, it's a quality operator only for vectors of the same element type. So even though string and const char star are comparable for quality, vectors of different element types are not. And the same is also true of different containers. So if I had, for some reason, a vector of string and a list of string, I could not say operator equal equal for those things. OK, so now you must be thinking, OK, time to use equal. So I can write, cout equal, TOS begin, TOS end, humans begin. And this will totally compile. But it won't do the right thing. That's undefined behavior. In our implementation, you get a cool debug assert if you compile this. But it's very bad. It could crash, return bogus answers, or work perfectly and then explode after you ship it to customers. So the correct thing to do is to use these new algorithms. Now if you call equal, TOS begin, TOS end, humans begin, humans end with an extra argument, this compiles and actually does what we want, which is awesome. And this extends to sequences of different types, like list versus vector or whatever. OK, so what functions am I calling here? What are the declarations? Well, back in CS+98, we had equal and mismatch. And of course, they take predicate if you want to use some sort of custom comparison. But they had this strange range and a half nature. That's what I call them, range and a half algorithms. Basically, the idea is, OK, you're passing me the first range. I don't actually ever need to compare an iterator from the second range. So why pay extra comparisons I don't need? I only need to take 3 iterators. And this is actually very harmful for correctness, as we've seen. CS+11 added is permutation algorithm mostly for the unordered containers, but it imitated the exact same interface as equal. So it's also afflicted by this problem. And then CS+14 adds these dual range algorithms also with predicate forms that we should be calling. So the difference in behavior is that if you're calling one of these range and a half algorithms, they assume that the length of the second range is exactly the same as the length of the first range. If the second range is shorter, undefined behavior as we saw. If the second range is longer, extra elements will simply be ignored because it's only comparing the prefix of that second range. For equal, this is basically never what you want. Same for his permutation. For mismatch, also usually not what you actually want. Whereas the dual range algorithms, they handle differently length ranges in a very natural way. Equals and is permutation, they're like, hey, ranges of different lengths, they can't possibly be equal. They can't possibly be permutations of each other. And the standard has a little extra optimization where if you pass some random access ranges, it can actually detect different lengths in constant time. We'll see how that's implemented. Mismatch is a little different. Basically, even if you have jagged length sequences, it marches forward, and if it finds different elements, then it returns a pair of iterators to them. If it gets to the end of one sequence and has exhausted that range without finding any mismatched elements, then the second sequence is going on. It will turn a pair of iterators to the end of the first range and the midpoint of the second range the same distance in. You could write it out on some graph paper, and it's basically what you want when you call mismatch, as long as you're expecting this behavior. So this is pretty cool. I recommend basically that you always use the dual range algorithms unless you know exactly what you're doing. As we've seen, the range and a half forms are very prone to misuse. And in fact, the dual range algorithms, you pay 0 or almost no performance penalty for calling these things. So you really should use them almost all the time. But it's not like the range and a half algorithms are wrong. There are cases where you really should consider using the range and a half algorithms. Stood list equality is an example. In this case, performance is absolutely critical because we're in the standard library, or maybe you're writing a high performance library of your own. If you gave bidirectional iterators to dual range equal, it cannot do the trick of sensing the different lengths in constant time because they're bidits and they're weak and stupid. But we have access in constant time to the size of the list. So we can do the length check ourselves, and then if they're different, skip calling the algorithm. But if they're the same, then call the algorithm. This is a use case for range and a half. But unless you're faced with that scenario, just call dual range equal in its permutation. So I promised we would look at the implementations of these things. Before we do that, let's look at the signatures of these things. So here are all the overloads of stood equal in CS Plus 14. We've got the classic range and a half in the predicate version, and then the dual range in the predicate version. So 4 overloads, 2 of them are totally cool. I've highlighted them in blue. The one that takes 3 arguments and the one that takes 5 arguments, they can't possibly be ambiguous with anything else. But the way I've laid them out here, you can see that there are 2 4-argument overloads. And remember that these are STL algorithms. They're templated. They take arbitrary types by value. So this actually leads to a problem. There's a classic example in vector where it has multiple constructors taking 2 arguments, one taking a couple of arbitrary iterators and one taking size t and const tref. So if you try to construct a vector int from, say, 11 and 1729, the constructor taking 2 iterators actually jumps into overload resolution. It's like, hey, I'm going to deduce init to be int. And I want to compete with the size t const tref constructor that you actually want to call. They're ambiguous. And the standard actually has to step in and disambiguate that using horrible 98 tech, or there's a better way in CS Plus 11. So my question for you is, are these things actually ambiguous? And does the STL need to jump in the implementation and manually disambiguate them? Or does some sort of magic mechanism step in and make these things unambiguous? So who is prepared to be embarrassed and thinks that these things are ambiguous? Raise your hand. OK, some people think. Who thinks that they're unambiguous by some magical mechanism? OK, a lot of people believe in magic. Very interesting. The answer is actually that they are unambiguous. And this is true for a very surprising reason, partial ordering of function templates. If I call these algorithms with, if I'm trying to call the old predicate 1.5 range version, I call init1, whatever those are, a second iterator, and then a predicate of a different type. So the overload taking init2 and bypred deduces the types that we want. The dual range version tries to deduce what init2 is, but it sees 2 arguments at the end of different types. And that won't pass template argument deduction, so it's just ignored. Whereas if I try to call the dual range version, the one that we want, succeeds in template argument deduction, the one that we don't want is also willing to deduce bypred to be init2. But the language and the compiler look and they say, hey, the one taking 2 init2s matches a strictly smaller infinite universe of types. So it's more specialized, and I want to prefer that because that's probably the one you want. And indeed, it is the one you want. This is not C++14 tech. This is not C++11 tech. This is a C++98 rule. People love to whine, oh, C++ is so complicated, it makes my brain explode, and with some justification. But when the complicated rules work, as they work in this case, it's really awesome. We just write the overloads we want, and their structure guarantees that they're unambiguous. OK, so now that we know we don't need extra enable if tech, let's think about other algorithms in the standard library. Here I did a little bit of original research. Are there any other range and a half algorithms that we need to be scared about? Now, a disclaimer, std copy takes 3 iterators, but it's not actually a range and a half algorithm merely because output iterators, for better or worse, they don't participate in ranges. You can't compare them. So can anybody, standard library implementers included, Marshall, think of other 1.5 range algorithms in the standard library other than equal mismatch permutation? Shout them out if you can think of any. I was not actually able to name these until I trawled the whole standard and looked at every algorithm and categorized them. Any ideas? There's one very important one. Transform, yes. Very good. Binary transform takes first one, last one, first two, and not a last two. I believe this one was missed because it writes to an output iterator, and the unary form is totally safe. But that binary form is still taking first two. In the future, I might actually write a proposal to deal with this, because this is a very popular algorithm and unsafe for the exact same reason. It assumes that first two is the same size as the first range. Can anybody think of any other algorithms? These are very obscure. Turns out there are some algorithms that morally write to output iterators. But in practice, they actually need stronger than output iterators. They need forward or bidirectional. And these are essentially range and a half algorithms, the backwards copying and moving algorithms and the swap, which wants to read. These really could take an extra iterator and do some bounds checking, and they don't. And then there's one more example that I found. Can anybody name it? Can anybody name what header it lives in? What header do algorithms go to hide? No, that's where all the algorithms, they're not hiding an algorithm. Numeric, where algorithms go to hide. There's inner product. And this is actually a very bad example because it is a classic. I just read from 2 ranges, and I don't write to output iterators or anything. And because it was hiding in numeric, the committee just missed it. When we were reviewing this paper, I didn't think of inner product. But there it is, and inner product is not defined for sequences of different lengths, so it really should throw an exception if it's given different lengths. So I might write a paper about this in the future. So be very careful when using these things, but for equal mismatch and permutation, please use the dual range forms most of the time. OK, so let's look at some implementation. Underscore capital identifiers everywhere are reserved for the standard library, so you'll see them used for our parameter names. Here is the dual range form that does not take a predicate. Please hold your questions till the end, and just remember the slide number. OK, so here is the dual range form. And previously, back in 2008, 2010, we actually copy-pasted implementations for the plain and the predicate form because we had no other way to do it. This was awful. At least once, I fixed a bug in, I think it was search n for the predicate form, and I forgot to hack the plain form, or vice versa. And even when we did make sure that these copy-pasted implementations were identical, it was slower to compile because we're spamming out so much code. So recently, we actually centralized our implementation so that everything is done in terms of the predicate form, and the non-predicate form simply calls the other one with a functor, these diamond functors that transparently apply some operator. So this is how we centralize them. We just call equal to diamond and give that to the predicate form. Now, here is the difference between the standard library and your own code. Your own code, you can do whatever you want. Awesome, unlimited freedom. In the standard library, though, our interfaces are mandated by an international standard. So this means that we can't go mess with the signature of global functions, even if we really want to. We have some more latitude with member functions, but not with global functions. We would like to use default template arguments and default function arguments to just say, OK, we're just going to define first one, first two, last two. Pred equals equal to diamond. And so if you don't provide it, you get the default arg. But that would mess with the signature, and we cannot do it in the standard library. We have to provide a wrapper like this. But you are not so constrained. You could use default template arguments and default function arguments for your own algorithms. And we've also got a funny trick to defend against ADL, which is usually our enemy. OK, so what does the version taking a predicate look like? Well, here's some more STL implementation. Now, I've seen threads on Reddit, and they're complaining, oh, STL implementations are all ugly. And VCs is ugly, and GCs is ugly. They're all ugly everywhere I see. And I mentioned, you're seeing it in every implementation. There's a reason. They have to do hard things. They need to protect themselves against macros. It's a fundamental reason why they're ugly. So here we got some debug checking. Ignore that. But at the end, you can see we're calling a helper function underscore is permutation with a couple itercat functions. OK, so what do these do? Here's its implementation. It's actually very simple. It doesn't really do anything. It's going to optimize away. It takes an iterator, and it returns an object of type name iterator traits iterator category. This is C++ 98 stuff. So given an iterator, it returns an object of type iterator category. What is that? Well, here's the iterator tag hierarchy dating back to 98. You got your input iterator tag, forward iterator tag, bidirectional, blah, blah, blah. These are empty structs. They are really boring, really simple, but they inherit from each other in a chain. And if you look at it, this actually matches the powers of iterators. Every random access iterator, like a pointer or a vector iterator, also has all of the powers of a bidirectional iterator. So the ranit tag inherits from the bidit tag, which inherits from the input, from the forward tag, from the input tag, and so on. And then there's the lonely output iterator tag. I could go on about that. Let's ignore that for now. So what does this stuff do? Empty structs and functions returning empty structs. Who cares? Well, this is used in a template metaprogramming technique. And Walter on Tuesday gave a wonderful talk about template metaprogramming. But one of the techniques that we use everywhere in the STL that he didn't have time to cover is called tag dispatch. That's being used here. So here our helper function is overloaded for all the arguments that we care about, plus a couple of empty structs, random access error tag. These we don't even bother naming the function parameters because they're empty structs and they do nothing. But we could say dummy1 and dummy2 if we wanted. So I've highlighted in blue the important code here. If we recognize that both ranges are random access iterators, we are actually required by the standard to check the lengths of the ranges in constant time. And we know we can do so with operator minus because we're looking at random access iterators. And if they're different, we just immediately return false for both is permutation and equal. But if they're the same length, then we need to do actual work. And instead of copying and pasting stuff, we actually call the range and a half version. So the check for the ranits, the first thing there, is mandated by the standard. Then when we call the other function to do work, we call the range and a half version. That is not mandated, but it's merely an optimization that I did when I changed this code. We've already checked that the ranges are the same length. So by calling the range and a half version, we avoid constantly checking whether the second range has exhausted itself. That's extra branches, and I don't know how you're using the STL's algorithms. Maybe you care very deeply that we don't pay extra branches, code gen, all that stuff. And so since it's invisible, we should just do the most efficient thing for free. Now, what if the user has disregarded Chandler's advice to always use vector all the time, and they're using something crazy like a deck or a list or a forward list? Well, is permutation and equal and all these other algorithms still need to work? So we have another overload of our helper function that takes two forward iterator tags, and it does actual work. Notice that I've highlighted here, it constantly needs to check every time it increments these iterators whether the first and whether the second range has exhausted itself. So you're going to pay more branches in addition to the expense of incrementing these iterators, but at least it gives you the correct result. And I've omitted some of the guts here just because the slide is already quite crammed. Now notice here that the overloads are only for ranit, and forward it. But this one here handles other combinations. Like if I give it a forward iterator and the second range is a bidirectional iterator, or if one is random but the second one is bidi, or vice versa. Overload resolution, thanks to this inheritance tag hierarchy, ensures that we basically do a cool if and test. If the first range and the second range are random, then call the overload that takes two random tags. If that's not the case, if one or both are weaker than random, then fall back to this forward case. Yeah, we're slicing the tags, but they're not virtual or anything. We don't care. So this is how tag dispatch works. Now, notice that this is sort of the most powerful form of tag dispatch that we use in the STL, dispatching on iterator strength. Usually, you don't use the tags if you're not working with iterators, but it's quite useful to be able to query some type trait, like is trivially copyable or whatever, and then call helper functions that are overloaded on true type and false type. That's why those integral constant things exist. Lots of people, again, they whine, oh, template metaprogramming, it hurts my head, let's ban it in our code base. And certainly, some template metaprogramming is mind-bending, like tuple cat is exceedingly difficult to implement. But really, 90% of the template metaprogramming we do in the STL is the moral equivalent of an if test. This is like really simple. It's like, if this iterator is random access, then do cool thing. Otherwise, do slightly less cool thing. And we have to write it in a weird form with overload resolution, and we write our things backwards, so things are declared before they're used. So the thing at the bottom ends up calling something at the top, so the flow of the if test is reversed. But once you get used to that sort of unfamiliar code structure, what we're doing is conceptually very simple. OK, so you notice here that although is permutation in particular is sort of a not efficient algorithm because it's worst case quadratic time, the standard still cares about performance. It's got to detect, hey, if these ranges are equal, then of course they're permutations of each other. We're required to detect that in linear time. And we do this by trimming matching prefixes. And even if we don't detect that they're equal, at least that reduces the n and n squared. So that saves us a lot of time. We have more tag dispatch, which I've not shown here. And this is not required by the standard. So if you're another implementer, maybe you want to add this optimization. If we detect that both iterators are bidirectional or stronger, we can also compare matching elements at the end and trim them off. That basically reduces the work, the hard work that we need to do to a central core of jumbled elements, and then we count matching elements and all that stuff. We could improve this further. This is one of my to-dos. We could actually match the prefix against the suffix and vice versa to detect reversed ranges in constant time. Maybe somebody cares about that. Hopefully not. But the standard library is where we get to micro-optimize everything as long as it's free. Equal also uses tag dispatch and other sort of compile time metaprogramming to detect, oh, I'm comparing consecure stars. I have a function for that memcomp, which spams out special assembly that's super duper fast. And we can improve this further. So those are the dual range algorithms. Please use them. OK, so let's switch gears and look at another CS+11 feature. Many people on the committee are very fond of allocators. We spend so much time in the library working group talking about allocator this and allocator that. Let's look at what std_allocator does, because this resembles a lot of the custom allocators that you may have in your own code. Here's std_allocator, and I've highlighted in red all these spammy type defs and helper functions that we don't actually care about 99% of the time. We're only really interested when we provide a custom allocator to tell it how to allocate and deallocate stuff. So these things in blue, allocate and deallocate, these are the things that actually do the work. Everything in red is sort of just extra bloat. But it was required by CS+98. You had to provide address and construct and yeah. Oh, and we're not done. We also need equal and not equal. It's just pages and pages of spam. These have really given STL allocators a bad reputation and a deserved bad reputation. They're spammy to provide. They've got to provide a whole bunch of extra stuff that we don't care about. So if you have any of your code base dating back before 11, they look like this. The good news is Allocator, the interface for allocators has substantially improved in CS+11. We call it minimal allocator interface. So now I'm going to show you something called the mallocator. This is a user-defined allocator that just calls malloc and free. So it's stateless. In your own code, it could be using some pool or something. But I just want to show you the minimal code necessary. The good news is that the complete class definition fits on a single slide, which is pretty awesome. It still needs a tiny bit of boilerplate. You need to provide a type diff saying what its value type is. You need operator equal, equal, and not equal. And of course, you need to be able to construct the thing. But you can actually focus the allocator down just to the allocate and deallocate functions once you've gotten that tiny bit of boilerplate out of the way. And then implementing allocate and deallocate is the same as usual. There's one new twist, though. In CS+11, there was a new exception type. It's called bad array new length. And you can throw this, which is derived from bad alloc, when you detect integer overflow. Allocators really should, because attackers love triggering integer overflows and causing bad math elsewhere in your program. You can throw bad alloc for it still, but bad array new length is more accurate. It says exactly what went wrong. OK, so there's actually a problem here. The STL needs to work with user code. And users, some of them are still providing CS+03 verbose allocators. They're expecting their special construct function, their special address function to be used. Other users, hopefully you, once you get back home to your code base, are providing CS+11's minimal allocators that don't provide things like address and construct, and they're only providing the functions that matter. How is the STL supposed to use things that might not be there? There's an extra layer called allocator traits, and it basically looks around a user-defined allocator and says, hey, do you have this function? If so, I'll call it. Otherwise, I'll fall back to a default implementation. Same for the type defs. And allocator traits detects this stuff automatically. So you should not provide a specialization of it. You really don't want to. Just let allocator traits do this for you. In that respect, it's somewhat different from iterator traits, which you can specialize if something does not have nested types. So how do we detect whether something is a nested pointer? Well, I was going to talk about Walter Brown's awesome Sphene trick, but he covered that on Tuesday. So if you didn't attend his presentation, please watch that. Really amazing trick. We use this in production now in VS14. So wonderful. And by the way, there's one interesting usage note. If you have a CS+03 era user-defined allocator in your code base, you had to provide construct. But in the new world order of CS+11, this is very bad. The old construct inhibits move semantics because it had to take const tref. There was no such thing as rvalue references back then. It was an older and simpler era. CS+11 construct takes perfectly forwarded stuff and forwards it down. Now, allocator traits, even if it's very powerful, using expression Sphene to figure out whether you provided a construct, it's still limited. We're not as, the library is not as awesome as core is. We can only sense whether a construct overload is present on your allocator. We cannot detect what it's going to do. So if you provide a CS+03 era construct looking like the one that takes const tref, allocator traits will say, oh, does the allocator have construct? Yes, it does. I'm going to call it. And then even if it's a vector of vectors that's reallocating, now you're going to copy elements. And you weren't interested in construct in the first place. So if you simply remove construct from your user-defined allocator, allocator traits will step in and perfectly forward. And this will actually increase the performance of your code for free. So please look at your user-defined allocator, and if you have a construct in there, remove at least that. The other ones are not super harmful, like destroy and pointer type def. You can leave those if you like. But really, construct has got to go. OK, so we're done with allocators. Now let's look at a feature with the associative containers. This is called, sort of a mouthful, heterogeneous associative lookup. So before we look at the containers, let's just look at the algorithms. This is a change between CS+03 and CS+11. Let's imagine you have a sorted vector. Here I've got a vector of strings. And this is sorted not lexicographically, not alphabetically, but by the length of the string. So short strings before longer strings. Now imagine I want to look up in this vector of strings where to insert a string of length 5. Or you can think of it as looking for the string of length 5. And if one doesn't exist, then show me where it would be. In CS+03, you actually could not do this. The wording was very muddled, but essentially lower bound, because it was a binary search, basically assumed that the sequence was sorted and that what you were looking for was of the same type. It wanted homogeneous types. CS+11 has evolved in a direction to handle types that differ. The element type it can be different from what you're looking for. Lower bound really just requires that the sequence be partitioned in some sense, that everything that's less than some element comes before everything that's not less than. Here, this is true. So I can compare strings and integers if I like, as long as I provide a function object that's willing to take these heterogeneous types. So now in CS+11, I can call lower bound, upper bound, equal range with things that differ in types. As an aside, this particular example is kind of silly. There's a new algorithm in 11 called partition point that does this, but simpler. If your sequence is partitioned, you can give it a functor and say, hey, where actually is the break between elements that are true in some sense versus elements that are false. But if you really do want to compare heterogeneously different elements, you can use lower bound. Now, you might say, oh, cool, I can do this in CS+11 with std lower bound. Hey, what about map lower bound? Well, not in C++11. So here's a motivating example, sort of unrealistic, but it does have analogs to real code. Imagine I've got a map from starships to captains. Starship, just for the sake of imagination, is some huge, horribly complicated class. It's got a registry number, which is really just a string, but it also has other stuff that's expensive to construct, and it's got a warp core and a sick bay and photon torpedoes and all that stuff. It's also comparable. The registry number field is special, because that's how starships are sorted by. If you compare two starships, you do less than on their registry numbers. The author of the starship has helpfully provided other operator less than overloads. So you can compare a starship directly to a register number, or even two registry numbers if you like. So in some sense, you can ask, OK, I've got a registry number. I would like to look up the captain that's associated with that. But take a look at the signature of map kvfind. It insists on taking const kref. In this case, it would be const starship ref. So if I just want to look up, OK, NCC 1701, do I need to construct a whole starship in order to look it up? And CS+9803 said, yeah, you do. Now you might say, OK, this example is unrealistic. The same is true of set starship or anything where you have a key type that's potentially large and it's sorted by something that is smaller than the whole object. This is very common. An employee, for a boring example, might be sorted by its name, but it might have extra fields in there, and you would have the exact same issue. You want to look up an employee by their name, and you don't want to construct a whole fake employee just to find where it is in your map or set. CS+14 has solved this. So here's the skeleton declaration of std map. It takes k, it's templated on k, and it's got a comparator less k, and all of its lookup algorithms take const k ref. And they have const overloads. In CS+14, they've gained templated overloads. So now it's templated on some arbitrary u thing. And these algorithms now take const u ref, and they will compare this u, which could be a totally different type, to the actual key type in the container. And this stuff exists on map, multi-map, set, multi-set. Okay, so how does this stuff actually work? Well, unlike most features in CS+14, this one is opt-in. The committee did not enable this by default, and this is for backwards compatibility. If we enabled the const uref overload, that could break existing code at compile time or at runtime or change the performance. So if you want to enable this, make sure that your key and this other type u are mutually comparable to each other, that the comparators behave consistently, that they don't return like, yeah, this is true, and then if you reverse it, yeah, it's still true. That would be bad. And you should avoid implicit conversions when you do such comparisons. They should compare directly in some sense. As long as that's true, you can enable it by saying map k of v and then less diamond. And these are the transparent functors that just directly forward whatever they're given, maybe different types, to operator less than. If you have a user-defined comparator, you can also activate this transparent lookup yourself. You just need to provide a nested type in your comparator is transparent that the STL will sense. It can be any type. It's unspecified. It just needs to exist. You could say true type or void or whatever you like. And by the way, people often ask, hey, what about the unordered containers? Did they get any love? And the answer is no. And it's not because the committee hates unordered containers. It's because it's actually an active problem that nobody has solved yet. The hash of a type, in general, can return different answers depending on the type. If I ask hash of short, given the value 5, and hash of unsigned long long, given the value 5, those can be different hashes. And in VC, they actually are. Hash does not behave transparently. Perhaps it will in the future, but until then, we cannot activate this transparent lookup on them. OK, so how do we actually implement this? Here's another little bit of metaprogramming trickery. Suppose you're faced with the challenge of you've got a class template. Here I'm showing you a very reduced and simple example, capital map. It is a find taking a fixed signature. The real map takes by constref. This fake map just takes by value. The structure is the same. You can ignore that. So my basic find just takes an int. But then I want to conditionally enable a templated overload, taking some arbitrary u. And I'm going to need to do this with some sort of bit of magic. And what I eventually want to see is I've got one struct, some key type, or actually, sorry, some comparator type named puppy, and another comparator type with this nested type def meow. I want the map to light up for things with a nested type def meow. So if I call find on something that's boring, like a puppy, that only the integer overload, the find int, is available. And this other find for u just removes itself from consideration. But if my comparator has this nested type def, I want the find templated on u to light up and participate in overload resolution. So if it's applicable, I want it to jump in and be considered. So when I heard about this feature in CS+14, we were working with Dinkumware, trying to get this in. And I was all ready to say, OK, I know exactly how to do this. I know how to sense for the presence of the nested type. I know how to use tag dispatch. I can totally do this. I'm willing to write just a ton of code, ton of spam. And PJ Plowger of Dinkumware said, oh, no, I can do this totally simpler. And I'd never seen this trick before. It's really elegant. I want to show you. What you might be tempted to do, though, it won't really work. So you might say, oh, I can just use Sphene with a default template argument. So you might try to write template type name u, and then type name some dummy equals type name c double colon meow. This is exactly what you do to constrain an ordinary function template, or even a member function where you want to constrain on u. But here we're doing something different. We're not trying to constrain this thing's existence based on some property of u, the thing being deduced on the member function. We're trying to make it visible based on some property of the type c, which belongs to the class, not the member function. Turns out compilers disagree. I asked with online compilers, all the 4 major front ends. Clang and VC think this is awesome. They totally accept it. EDG and GCC reject it. I asked our compiler devs, and they said, yeah, we're a little worried by this, but yeah, we think EDG and GCC are correct and that this code should be rejected. I talked to Kling's devs, and they also think that this code is ill-formed and should be rejected. But if you're only testing on one compiler, you might write this, and then you'd have a portability headache. The problem really is that C is seen very early, and the compiler tries to substitute it in and just explodes horribly. This is what happens when you try to write code at the frontier of C++. But there's a way to avoid this, and this is what PJ Pliver showed me. You can do it with just one extra line. What he did is he said, OK, template type name U, and then he adds another template parameter, type name C2. And he defaults that to C. This is the comparator that belongs to the map. And then he constrains it with type name dummy equals type name C2 double colon thing I'm interested in. An extra layer of indirection solves this problem. When the compiler sees this, it looks and says, OK, template type name U, I don't know what that is yet. Template type name C2, I don't know what that is yet either. I see that you're defaulting it to C, and since I'm parsing some instantiation of map, I know what that is. But the user might pass something different there, so I'm not really certain what C2 is going to be. And then you're trying to grab something from C2 named meow. Well, I don't know what C2 is, so I'm not going to explode yet. I'm only going to try to figure out what C2 meow is when somebody actually calls find view. And at that point, then the compiler will realize, oh, you passed me U, and I don't know what C2 is, so I'm going to use the default. Then it tries to substitute it in, and if C does not have meow, then it explodes or not, and the thing is visible. Every compiler accepts this. This is a very nice way to make a member function disappear based on some property of a template argument belonging to the class. So if you're ever faced with a similar situation in your own code, you can use this trick. It's very portable, very nice. OK, so the last feature I want to show you before I get to Herb's bonus slide that he asked me to include is const rvalue references. So we all saw Scott Meyer's presentation talking about, hey, what does autorefref do? What does trefref do? But there's this one thing that people sometimes try to use, and it explodes, and then they learn not to use it. And these are const rvalue references. It certainly is the case that you should not use these things most of the time. But before we get to that, let's look at a motivating example. Now, I wrote this code at home, and I had it checked in for years until I realized that there was something wrong with it. Here I've got a regex. I'm looking for file names, the form meow, and then some digits, .text. And then I'm iterating over a directory using Boost File System, which is really cool. And I want to get the directory iterator that's iterating over my directory, extract the path from it, get only the file name, not ctemp, blah, 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 and then convert that to a string, and then match it against my regex. And then if it matches, I can crack it open and look at the number in the file name and then go do something with it. This actually works most of the time. But it triggers undefined behavior in CS+11. And in 14, they fixed that, and it's now a compiler error. Anybody tell me what's wrong with this code? Why is it bad? You don't count. You're an implementer. Yes?
The match points into the temporary string that died.
Yes. Dot string returns a temporary stood string by value. And this would be OK, except that it fills the match results. If you haven't used the regex library, this is basically a vector of pairs of iterators into your string. So when I say m bracket 1, I'm accessing pointers to a temporary object that was constructed on the previous line and destroyed at the end of that full expression. So if that memory has been reclaimed, then it could be filled with garbage. This is very bad. And yet, it compiled with Boost and CS+11. It had to compile and typically would not even trigger a warning. And yet, it triggers undefined behavior. But now, with rvalue references, we have the technology to detect temporaries and reject them at compile time. This is why it is a compiler error in CS+14. So the original overload sets that we're all used to, they're still totally valid. Move semantics, you overload on constxref and xrefref for a specific x that's not templated on the actual function. Then we're familiar with the perfect forwarding overload, where we have template type name t, where t belongs to the function template. We take some arbitrary trefref, we forward it down, and we preserve the original CV qualifiers and the value category, the L valueness or R valueness. In neither of these overload sets does the type const xrefref or const trefref ever appear. Some people are like, oh, const is good. I should just slap it on move semantics and perfect forwarding. And no, it totally breaks these overload sets. Do not use it there. But it can be used to detect temporaries. So here is what I think of as the third new overload set that CS+11 added. If you overload one thing that's good, that takes const xref, that will take both modifiable and const L values. L values are expressions that are persistent in some sense, often names, but also like, array bracket 0, something you can say over and over. And you can get pointers into them, and those pointers will be to things that hopefully will live a long time. But if you're past temporaries, then you have another overload. Foo taking const xref ref, and you delete this one using CS+11's deleted functions. This ensures that if the user gives you an R value, some sort of temporary expression, that it is absorbed by this deleted overload, which will trigger a guaranteed compiler error. This says, you're giving me a temporary, but I want to get pointers or something into this thing, and that temporary is going to be destroyed really soon. So maybe you should rewrite your code. You can also template this without harm. Unlike the move semantics overload set where trying to template it gives you trouble. Here it's totally fine to template it and take const ref ref versus, or take const ref, which is good, or const ref ref, which is bad, and delete it. The STL now uses this in more places. Back in CS+11, the function cref, which creates a reference wrapper, that stores a pointer into the thing and basically automatically dereferences it whenever you use the reference wrapper. It would be very bad to get a reference wrapper to a temporary that's just going to evaporate instantly. So cref is overloaded with this templated form so that it rejects temporaries on site, will not compile. In CS+14, regex match, in the scenario that I showed you, is now overloaded on constring ref, which is good, and constring ref ref is deleted. Because if you give me a temporary string and a match results, I don't want to fill that match results with iterators into that temporary string. You're probably going to try to dereference them. That would be bad. And regex iterator, because regexes are quite expensive to copy, it actually stores pointers to the regex it was constructed with. But it doesn't want to modify the regex. So in Boost and CS+11, it was constructed from const regex ref. People were tempted to say, oh, let's construct a regex iterator from regex parenthesis double quote, meow dot star, whatever. And that's a temporary regex. So as soon as you try to use the regex iterator, uh-oh, its regex has evaporated and crash. Now we reject temporary regexes in the standard. OK, so the bonus slide that Herb wanted me to include is a little bit more about auto ref ref. And I'm also going to talk about const auto ref ref. So people are sort of overwhelmed when they hear about auto. And I just want to sort of simplify things for you. Here are all the scenarios you can use auto in range-based for loops and in variable declarations. I've been on a crusade against auto elem and const auto elem in range-based for loops. These things are bad. They copy elements. You do not want to copy elements when iterating over a range. Nobody ever wants this. If you want to, actually copy it visibly in the body. You don't want to do it implicitly in the range-based for loop. So I feel like physically sick if I try to type auto elem colon range, even if it's just like a vector int. Like, just please don't do it. Just recognize it as bad code. Instead, you always want to iterate over ranges with auto ref or const auto ref if you want to apply constness. Auto ref also works with const ranges. You get a const x ref. It's totally cool. But sometimes you like to explicitly apply constness. You can do that too. Auto ref ref range. Herb wanted me to say, and I agree, that this is valid. But it should be used very rarely in a very obscure scenario. You're working with some generic container, which might be a vector bool, and autorefref will be willing to handle vector bool's stupid reference proxy. But aside from that very specific example, which is experts only, you don't need the full power of autoref. Just use autoref or const autoref, and you'll get a compiler error if somebody tries to give you a vector bool. In CS+17, const autoref is just nonsense. Don't use it in range-based for loop. It does nothing. You don't want that. In CS+17, all that goes out the window. You can use the new range-based for loop and just say for elem colon range. It works in place, even works with vector bool. Uses autoref under the covers, ignore that. Super awesome, super terse. For variables, situation is a little different. If you want to copy a variable and say auto a equals stuff, totally cool. You can also make a const copy. That's also cool. You can store a reference or const reference to a thing, also good. Autoref to bind to arbitrary stuff, again, this is really rare, really experts only. Yeah, the range-based for loop uses it in a couple of places, but this very rarely comes up in your own code. In your own code, you usually have some idea of whether what you're getting is an L value or an R value, and whether you want to make a copy or not. Very rarely do you need the full power of autoref to bind to arbitrary anything and suspend it in midair. So please don't use that by default. Only use it if you need it. And again, const autoref, I thought about it, makes absolutely no sense ever. You never want to do such a thing. OK, so we managed to finish about 10 minutes early. Does anybody have any questions? Please come up to the microphone if you have any.
Hi.
Yes, sir.
Slide 45.
45. Excellent. Don't have to go back. Oh, it's a title slide. OK.
Oh, was it? Oh, OK. Well, 44 then?
44. OK.
Is it possible for me to use the Const T ref technique to prevent, if I've got like a number of classes that kind of like point back to each other?
OK.
Is this something I could use in VS 2013 U3?
Yes. Overloading on const ref will totally work in VS 2013. Anything that supports rvalue references will reject temporaries like this, and cref in 2013 does exactly this.
OK.
All the other features I talked about, like the dual range algorithms, those are all implemented in VS 14.
OK.
The minimal allocators is partially implemented in 2013, but we missed a few places, like string and debug mode, I believe. That's all been fixed in 14. But this particular one, this is so basic that we supported it years and years ago.
Awesome. Thanks.
Sure. And in fact, I believe even 2010 is capable of this. But nobody should be using 2010. Please upgrade. Please, please. Any other questions? Oh, yes.
I think it's slide 22.
22.
Could be wrong.
Okay. Well, I'm just going to go back. I'm afraid to get out of this presentation mode. Otherwise, I might have trouble getting in. OK, so forward, yes.
On the for loop, the void after the comma.
Ah, yes, that's my little trick. So turns out, I even included a little bullet there, but I skipped over it. So we know two facts. One, the core working group hates the library working group and won't give us fun toys to play with. So we have to do all this metaprogramming tech. Fact number two, users hate implementers, and they always want to make the implementers' lives difficult. In particular, they like to overload things like operator address of and operator comma for their own types. And then they file a bug, and they're like, oh, I overloaded operator comma, but look, nothing in the standard prevents this from working. So you need to tolerate overloaded operator comma on iterators. And sometimes we like to say things like plus plus it 1, comma, plus plus it 2 in a for loop where we wanted to stick a single expression. If those are user-defined types and operator comma has been overloaded in that namespace through ADL, it'll pick up that overloaded operator. That's not what we want. So in 14, I went through and I audited every STL algorithm with every combination of iterator powers and fixed like over 100 occurrences of plus plus it 1, comma, plus plus it 2 by inserting a void cast. Turns out if you cast one of the operands to void, users cannot hijack that no matter how much they want. So that's what that little bit is doing there. Ultra generic code needs to do this. I guarantee you Boost has not done this. Possibly even other STL implementations, but VC will now tolerate your overloaded operator commas, and I hate you.
So presumably, if you have several commas, you would need to do the void on every one of them. And why not do the void on the first one?
Not true. Oh, but that's an excellent question. So occasionally we do have plus plus it 1, comma, plus plus it 2, comma, plus plus it 3. We have no occurrences of 4 in the STL, but 3 occasionally occurs. Turns out in the case of 3, inserting the void cast in the middle is sufficient to defend both of them. If you look at how the precedence works, it's left to right associative. The first expression has a second operand or type void, must be built in. And then the type of that thing is the type of the second operand. So the whole expression type is void. And then we evaluate the second comma. And then you have a left operand of void and a right operand of stuff. So a void in the middle is sufficient to defend against 3. And the reason why I do this, even for 2, is because I consider it to read clear. It is absolutely true. I could cast the first operand of void, even with a CCast like that. And it would be absolutely unambiguous and defend against overload operator comma. But even though operator comma has the lowest precedence, much lower than casts, paren void paren, plus plus it 1, comma, plus plus it 2, it doesn't visually look like the void is evaluated before the comma. And I consider it visually unambiguous to stick it in the middle. We do, if you look at our sources, we do cast the first operand void only when we need the result of the whole expression. In that case, I will cast the first one. But yeah, that's an excellent question. Yeah, question?
There are parens around the return expression.
Yes, that is Dinkumware style. Bill likes his parens. And I rigorously enforce that standard. My own opinions differ. But our implementation does that.
Even still in the light of decal type auto?
We do not use decal type auto in our implementation yet. But if we do in the future, and we return a local variable, we will be aware of potentially returning a reference. The good news is that although that seems very scary and dangerous, compilers are totally willing to warn about returning a reference to a local variable in that scenario. So in practice, as long as you compile at a good warning level, that's not really a danger. Yeah.
What's the advantage of this?
Advantage of that, it makes Bill Plogger happy. It's his code base, it's his style. Like, I'm very particular. I like to brace all my stuff. I hate tabs. I like the one true brace style where braces go on their own line or on the same line as the other stuff, and you say brace else brace on a single line. I just consider it compact. And Dinkumware likes a different style. I don't super care, but files need to be consistent. So within a single file, everything needs to follow the same conventions, and our convention in the STL is parenthesize everything. And braces on their own lines, tabs, that stuff. It doesn't really matter. We just try to be consistent with ourselves. Cool. Any other questions? Yes?
This is probably a little off subject, but you mentioned you purchased or licensed the library from Dinkumware.
Yeah, that happened back in the mid-90s. I think it was like 96 that Microsoft licensed the STL from Dinkumware.
Could you just speak to that a little bit? What is your
Microsoft's best decision ever.
Relationship with Dinkumware? And
we've worked continuously with them since 96 or whatever, long before I joined the team in 2007. And we've received updates, bug fixes from Dinkumware, one of the few, and I think maybe the only remaining company selling a commercial CS+ standard library. There used to be more back in the day. I'm convinced that if Microsoft had tried to write their own STL back in the mid-90s, it would have been awful. Dinkumware has the expertise to write this in a really high-quality manner. Bill Plogger has been on the committee for a very long time, designed a whole bunch of stuff, implemented almost everything. And that depth of expertise, yeah, Microsoft is just really lucky to be able to work with them.
But you are obviously implementing a number of
yes, my job is very strange. Really, my job is that of code reviewer. That's sort of my primary job. I review everything that gets checked in for correctness and performance and all that stuff. I fix Microsoft-specific things like calling conventions, CLR call, everything relating to DLL, stuff that's not portable, that's Microsoft-specific. I end up working on that. I add minor features based on who's busier at the time, and features of my own design, like the diamond functors, the transparent operator functors. Like in this case with the dual range algorithms, Dinkumware added the dual range algorithms, and then I went in and cleaned up some things. Like I tweaked the detection and constant time of random access iterators. That was missing in the original code. It's really easy to miss that sentence in the standard. But as I was reviewing it, I was like, oh, we need to detect randits and constant time. I can add that. So I don't write code very fast, but I write it very precisely. And so I work very well with Dinkumware.
Okay, that makes sense. Thanks.
Thanks. Question?
How do you test all of this?
How do I test all this? Not as frequently as I'd like. We have internal test suites. We call them DevCRT and TR1. And we license comprehensive suites. We also have recently started using libcs+'s test suite, which has some Linuxisms, but it's mostly applicable to us. The most valuable test suite I think we have is this DevCRT thing, which despite the name is mostly for the STL now. It's basically a collection of every bug we've ever fixed. We usually add a regression test for it if it's strange. And these tests stress the weakest areas of our STL, the most bizarre code like overload operator comma, or weird things with maps of tuples of vectors and rvalue references. And they tend to expose fragile parts of our implementation. We make sure that we don't damage them. And importantly, we make sure that the compiler devs who are churning the layer underneath us don't break us. And this test suite also provides most of our coverage for bizarre compiler options. Like I said, users hate us, so they compile with /gr, gz to change the default calling convention. They compile for x86 and x64 and ARM and all this stuff. And so our test suite can be run automated on these platforms with these switches and detect, oh, wow, you forgot a calling convention there, you forgot inline there. It's very easy for us to do tiny things like slip up and forget to mark a header-only function as inline, which is totally cool as long as you only have one source file. And then as soon as you try to drag it into two source files, it explodes. So we have a test that includes all STL headers in 2 translation units and links them together. So that's how we detect a lot of our bugs in automated fashion. Cool. Any other questions? Thanks.